Righty, good day, Matric. This will be your last integration video, and then we are done with paper one. Hallelujah! So, you need this worksheet, which I'm going to show you now. I sent it to you on WhatsApp and on Teams. That's using the definite integral to solve volumes of solid revolutions. Okay, it comes from the Evans. The examples come from the Evans AP textbook, page 82 to 84. Right. Okay, so yesterday we looked at the development of the formula, which came from forming kind of like a Riemann sum, if you remember, forming a whole lot of disks, letting n tend to infinity, and then finding an infinite sum of all of the volumes of all of those individual cylinders. And from that, and remember the infinite sum is an integral, okay, we end up with this formula that the volume, if something's rotated about the x-axis between x is equal to a and x is equal to b, if a solid is formed by rotating a curve about the x-axis, remember as the line moves it's creating a solid, okay, between x is equal to a and x is equal to b, then its volume is defined as the integral between a and b of f of x squared with respect to x times by pi. Okay, on the formula sheet, this is what they give you. Okay. So, and guys, remember with definite integrals, okay, especially in applications like in volume, you must always use your calculator, the integral function of the calculator, unless they specifically tell you not to. Okay, there are some though, okay, when you're developing formulas, for instance, okay, as you'll see later, where a calculator is not going to really help you. Right. So the first question is, you've got a function f of x is equal to 2x plus 1. Okay. Between 0 and 3 is sketched below. So guys, first of all, if you can imagine, what's that solid going to look like? You need to get a picture in your head of what that's going to look like. And what's going to happen is that rotates around. So you're going to get kind of like a cone, truncated cone, which is going to look something like that at that end. And then it's going to go all the way up to here. And be symmetrical about the x-axis. At the end, you're also going to get a round kind of thing, and the opening of the cone. So that'll be what the solid looks like. And we need to find that volume. Okay. So to find the volume. Okay. So that's A. That's what the solid would look like. I hope you can get some kind of picture formed. You'd have to look from the side down to see what's going on there, really. Right, so to determine the volume generated by f of x is equal to 2x plus 1 between x is equal to 0 and x is equal to 3, well, it's really easy. Okay, the volume will be equal to pi times the integral between, or what the x values we're working with, between 0 and 3. Between 0 and 3, those are your upper and lower boundaries. What is the function? 2x plus 1 with respect to x. Right, so you can just go use your calculator at that point. Just for fun, let's just do 1 though, okay, without a calculator, just to get our head back into it. So the volume is going to be equal to pi. The definite integral of x, 2x plus 1 is going to be x squared plus x. And if you differentiate that, okay, you get I've been a complete dumbass. Hopefully you spotted it. Okay, it's f of x, I'm using this formula. I often do this. Volume is equal to pi integral between a and b of f of x squared with respect to x. Okay, integral between a and b of f of x squared with respect to x. So I left out that squared. Okay, so to be quite honest, okay, you can go times that out if you want, but actually let's just do it. Okay, time is short. Okay, on your calculator. So on your calculator, you'll simply go. Okay, and let's say to you do it without a calculator, which you should be comfortable with doing. You're going to go the integral of 2x plus 1. Just do this with me, please, on your calculator. Just make sure you're comfortable with it. 2x plus 1, not 19, 2x plus 1 all squared. Okay, from x is equal to 0 to 3 equals, okay, and you get 57. So its volume is going to be pi times 57. Okay, and so it's going to be 57 pi, and the 4 scarer screams at me, 57 pi units cubed. Okay, so there's your answer, 57 pi units cubed. As I say, if you had to do it without a calculator, okay, you'd just go volume is equal to pi. The integral between 0 and 3, you'd have to square that out. So you'd get 4x squared plus 4x plus 4 with respect to x. Okay, and then if you're going to integrate it, it'll be volume is equal to pi times the integral of 4x squared is going to be 4x cubed over 3 plus 2x squared plus 4x between 0 and 3, okay, which would be equal to, okay, then you're going to go sub in 3, so the volume would be 3 cubed over 3, which is plus 3 squared plus 4 times 3 minus, well, if I sub in 0 into all of those things, it's just 0, and I've still got to times it by pi. And if you go check, you'll get 4 times 9, which is 36. 3 squared is 9 plus, I've made some mistake somewhere. 3 squared is 9 plus 9 plus 18 plus 12, okay, which is going to be 36, 48. Where have I gone wrong? Okay, 4x cubed over 3 plus 2x. I'm on crack. Sorry, guys. Plus 1 was over there. Oh, that's another skill, is being able to autocorrect. Okay, so plus 3. So it's going to be plus 3, which is 36, 44, 54, 57. Okay, so it's equal to 57 pi units cubed. Right, so if you're asked to do it without a calculator, remember that's the process that you go through. I'm not going to do any more without a calculator, okay, unless we're working with variables, then you're going to have to. But if they don't say without a calculator, just lob it into your calculator. Right, don't forget, the biggest mistake I find, which I often do, as you've seen already, is I forget to do the square in there. But the formula is f of x all squared, so be careful of that. Okay. Righty. The next one, it says you've got a function y is equal to this curve over here is g of x is equal to 2x cubed plus 2x plus 1. Sounds of Joburg in the background. Okay. It says try imagine you've got it's drawn between 0 and 2. You've got to try imagine a solid generated by rotating g about the x-axis between x is equal to 1, which is over here, and x is equal to 2, which is over there. Okay. And if you rotate it, so it's all going to be symmetrical, so somewhere around about there. Okay, that was around about 3, I think. Okay, so something like that, doesn't have to. So the solid would be formed like that, and if you can imagine, well, the whole thing, if it had gone on forever, would look exactly like a vuvuzela. This is kind of like a vuvuzela where you chopped off that bottom bit over there. So that's your solid formed by rotating about the x-axis between 1 and 2 is what the question says. Okay. So determine the volume generated by rotating it when x is equal to 1 and 2, corrected 2 decimal digits. Okay. So you're going to go the integral. Okay, volume, let's just write the formula down so we don't make careless mistakes. Is going to be equal to pi. The integral between a and b, on the formula sheet it says y squared with respect to x. So it's going to be equal to pi integral between 1 and 2 of x cubed plus 2x plus 1. Don't forget to square it with respect to x. Okay, and if that now we're just going to shove into your calculator. So go do that for me, please. So you're going to get pi, let's do the integral bit first. The integral between of what? Of x cubed plus, I should need a bracket, x cubed plus 2x plus 1 all squared. So going from 1 to 2, bing, and we get that funny number over there, which is 66,7. So and then I have to times that by pi. So times by pi equals, and that's it to 2 decimal places. So it's 209,78 what units cubed. I don't care. Okay, so easy peasy, lemon squeezy. Alrighty. Okay. Now we talked about area. Okay. So here on the note it says, okay, finding the volumes of solids generated by rotating the area between two curves about the x-axis. So say we wanted some weird looking solid, if you can imagine it, formed by rotating the shaded area about the x-axis. Okay, quite difficult to picture. Okay, it's a hollow thing in the middle. Okay. So remember, when using integration, when we were finding area, if I was finding this area between these two curves, I could do it in one step. Okay, I could take, let's just have a look at the notes. When using integration to find the area between two curves, f and f, so I'm looking at area here, not volume. Okay, f of x and g of x between x is equal to a and x is equal to b. So in this case, that's between there and there. Okay, where f of x is the top curve and g of x is the bottom curve. This can be done with a single integral. So area, guys, if you're finding the area bounded between two curves, you can do it as a single area. Okay, the area is equal to the integral between a and b. What are a and b? Your points of intersections of the curve. Okay, of the f of x is the top function, whatever the top function is, minus the bottom function. So it's quickest to do it in one step. Okay, because with area, it's pretty easy to visualize. If you wanted to find this shaded area, if you found you could do it separately as well. It wouldn't be wrong if you did it separately. So if you're in doubt and you can't remember what to do, or whether you're finding the area of a shaded region between curves or the volume, do them separately, you'll always be right. Because if you do the area in two steps, what would you do? You'd find this area, okay, of the top function. That would be this whole shaded region over there. Then if you find the integral between there and there, you'd chop out the bottom bit and you'd be left with the shaded bit. But you can do it all as a single function when you're doing area. However, okay, when you're finding volume, okay, so it can be done, you can do it in one step when you're doing area. When finding volume, however, okay, of a solid, okay, you cannot, is the key idea, find the volume, okay, by using a single integral, but instead have to find the volume generated by the top function minus the volume generated by the bottom function. Okay, in other words, you have to do two separate integrals. Okay, can't do it as a single integral. It's important to remember that. Okay, you could always do the area, as I said, you could always find area. If you did them separately, it's also fine for area. But volume, you've got no choice. You've got to do them separately. You can't do it as one integral. Okay. So it says you've got a function here. Just be careful, don't use the wrong one. The top g of x is equal to 4 minus x squared. Is this blue one over here? And the red one is f of x is equal to, straight for you, f of x is equal to 2x squared plus 1. Okay. And first question says, find the volume, not area, okay, generated by rotating the area of the curves between f and g around the x-axis. So, first of all, okay, I know you can see it from the graph here, but I want you to get used to you're not in an exam, you wouldn't probably be given those points over there. So first of all, what you have to find is the point of intersection of the two curves. So your point of intersection is going to happen when f of x is equal to g of x. So in other words, when 2x squared plus 1 is equal to 4 minus x squared. So you're going to get 3x squared is equal to 3. X squared is 1. And as you can see from the graph, x is equal to plus or minus 1. Right, so always make sure you found the point of intersection unless it's specifically given to you. In case like that, it will be given to you, but just to show you. So now, you've got to, first of all, the volume is going to be the volume generated by the top function minus the volume generated by the bottom function. Okay? Got to do them separately. So the volume generated by the top function, let's do that first. Okay, is going to be the integral between negative 1 and 1. What is the top function? Top function is that one over there, which is equal to 4 minus x squared. Now be careful. Remember your volume formula, it's that function. Again, what I said, always forget 4 minus x squared squared. And usually about 10% of candidates forget the square. Okay, so 4 minus x squared squared with respect to x. So the volume of the top function, go shove that into your calculator. I'm going to cheat, and you should get a solution. You should have done that on your calculator by now. The volume of the curve above, negative 1 and 1, or 4 minus x squared squared. You should get 406. Okay, it's pi times that, sorry. Okay, so the volume is equal to pi times the integral between minus 1 and 1 of 4 minus x squared squared with respect to x. And you should get an answer of 406 over 15. It's quick to do it myself. 406 over 15 pi, I'm looking at my memo, units cubed. Right, so that's this volume if you rotated that curve, the blue curve, about the x-axis. But now when you look for the volume of the bottom function, okay, we're finding that the volume generated by rotating the bottom function. So it's going to be pi integral between minus 1 and 1. The bottom function is 2x plus 1 of 2x plus 1 all squared with respect to x. So the volume of the bottom function, let's do that one on the calculator. So we're going to go, okay, we've got the integral, let's do it in one, no, let's not freak the calculator out. The integral between of 2x squared plus 1 all squared of 2x squared plus 1 all squared, and don't forget that squared, between minus 1 and 1 equals, and you get 94 over 15 times pi is 94. Always leave things in pi form, guys, unless I specifically tell you otherwise. Leave it in pi form. So the volume of the bottom generated by rotating the bottom curve is that. So your total volume, if I go back to this, is going to be the volume of the top function, which is 406 over 15 pi minus 94 pi over 15, and 406 minus 94. If we simplify that, it should end up, you can check, the volume is going to be 104 pi over 5. It simplifies to that. Units cubed. Okay, and there's your final answer. If they leave it like that, if they said give it to 2 decimal places, you've got to work out whatever it is. Okay, so volume, got to do them separately. Okay, the volume generated by a shaded region bounded by 2 curves. What's the process? Find the point of intersection. You cannot do it in one step. You cannot take the volume of the top minus the bottom volume. You can only do that for area. Okay. Work out the volume of the top function. Don't forget the squared minus the volume of the bottom function. Okay. Take them away. Okay. And you've got the volume that is required. Okay. Cool beans. Righty. Okay. Yep. Right there. The answer 104 pi over 50. Right, I think this came from a past paper. I'm not sure. All right, so question 4. The shaded area bounded by the curve, well, here's the curve y, there's a parabola part of the curve. There's y is equal to a half x squared. This over here is the line y is equal to 2x. First question, find the coordinates of P. Okay. Well, assuming we don't have axes here, okay, it looks like we should get an answer around about 4, 8, but let's check. So your point of intersection is going to happen when 2x is equal to a half x squared, okay, 2 divided by a half, 2x is equal to half x squared, 2 divided by half is 4, so when 4x is equal to x squared, so when 0 is equal to x squared minus 4x, which gives you 0 is equal to x minus 4, so in other words, when x is equal to 0 or x is equal to 4, which looks right. So at P, the x coordinate is 4, so therefore the y coordinate of P is equal to 2 times 4, which is 8, so P is the point 4, 8. Easy peasy. Right, so that's A done. P is the point 4, 8. B, determine the area, not volume, the area of the shaded section. So you could do them as separate curves. So you could either go the integral between A and B. So you could do it like this. You could say, you can check that you're going to get the same answer. You could, one way you could say it's the area is equal to, area now, so it's not squared, the integral between A and B, and we're working between 0 and 4. Okay, and you could do the top function, which is, in this interval, is 2x with respect to x, okay, minus the integral between 0 and 4 of a half x squared with respect to x. So you could do it like that. You could do them separately. It's quicker, though, probably to just do it as a single integral, which you're allowed to do for area. So the area is going to be the integral between 0 and 4 of 2x minus a half x squared. Don't square it, it's just area. Volume, you do that squaring and times it by pi. Okay, and if you go work that out, the integral between 0 and 4 of 2x minus a half x squared with respect to x, go check on your calculator. You're going to get 16 over 3. This is area. So it's going to be, what's it going to be, Scara? Good, units squared. So your area of that shaded region is 16 over 3 units squared. You can do that as a single step. That's the only difference really between, that's the key difference between area and volume. You couldn't do that with volume as a single step. Right, C. Now you want to form a solid generated by rotating the shaded region. So with volume, key idea, must do the integrals separately. Must find separate volumes. So your volume is going to be the volume of the top generated by the top curve minus the volume generated by the bottom curve. Okay, the volume generated by the top curve, don't forget your formula. Volume is equal to pi integral between A and B of y squared. Okay, don't forget the squared with respect to x, and don't forget the pi. So the volume of the top function is going to be the integral between 0 and, so the volume of the top function is the integral is pi times the integral between 0 and 4. Top function is 2x. You've got to square it with respect to x. So that's the volume of our top function. Okay. Minus the volume of the bottom function. So it's minus pi integral between 0 and 4. Okay. The bottom function is a half x squared. So that's, sorry, we're doing it separately. So the volume of the bottom function is equal to that. Okay, a half x squared all squared. Okay, with respect to x. Okay, shove those into your calculator. Okay, and the volume of the top function, integral between 0 and 4 of 2x all squared, in other words, of 4x squared, you should get an answer of, you can go check on your calculator, 256 pi over 3 units cubed. So that'll be the volume generated by that straight line, and the kind of cone, well, it would be a cone. Okay, and the volume generated by the bottom function, which would look like a vuvuzela. Okay, so you can take the top volume minus the bottom volume, would be equal to, you're going to get the integral, you should get 256 pi over 5 over 5 units cubed. So they're the same, but the one's over 3, so therefore your volume is 256 pi over 3 minus 256 pi over 5. And you should get a final answer then of 512 pi over 15 units cubed. Okay. So there's your final answer, 512 over 15 pi units cubed. Okay. Right. Last one, I think. Okay, and these are the funnest ones. Formulas that you've seen your whole life and you thought people got them by getting hammered in a bar one night, and then just coming up with some kind of nonsense. In fact, come from this volume of integration. So it says, we want to, basically the objective here is, okay, determine the volume of a sphere radius equal to r. That's the objective. Okay. Find the volume of a sphere, radius is equal to r. You should have come across it at some point in your life, and the volume of a sphere is 4 pi r cubed over 3. So we're trying to prove that formula. Okay. Nice question would be to say, use integration to prove that, I wouldn't give you any steps, to show that the volume of a sphere with radius r is 4 pi r cubed over 3. So how would we approach it? Well, we'd have to first figure out a function, okay, that we could rotate about the x-axis in order to generate a perfect ball. So what we'd have to do, well, let's think about it. It's got to be a semicircle, obviously. Okay, it's got to be a semicircle. Okay, and that's going to go from negative r to r, because your radius is equal to r. Here's your x-axis, here's your y-axis. You rotate that semicircle, what you're going to get? You're going to get a perfect sphere. Right, so now that's your first step. Figure out what the function is. The next thing is I have to figure out what's the formula for this. Okay? Well, if you remember, if you forget it, it's quite easy to remember. A circle has a formula x squared, center origin, x squared plus y squared is equal to r squared. So if you split this up into bits above a semicircle, well, that's still a circle, y squared is equal to r squared minus x squared. And you can then split that up into two semicircles. The one below the x-axis would be y is equal to negative, because y would be plus. This is still a circle over here, guys. Y is equal to plus or minus. That's still a formula for a circle. Okay? Still a circle. Okay, so I can then split that up into two semicircles. Okay. The one below would be negative r squared minus x squared. Okay. The one above, which is the one we're looking for, the formula for this semicircle would be y is equal to the square root of r squared plus the square root of r squared minus x squared. So that's the function, okay, the formula for this function. You can see it is a function. Okay, they've asked us over here to state the equation of the function f. It would be f of x is equal to the square root of r squared minus x squared, and it's one-to-one. It's not a one-to-one, many-to-one function, but it's a function. Okay, so now I've got my function. Okay, f of x is equal to the square root of r squared minus x squared. Now it says use integration to prove that the volume of the sphere is 4 over 3 pi r cubed. So what are we doing? We're going to use our formula. Volume is equal to pi integral between a and b of the function squared with respect to x. In this case, volume is going to be equal to pi, where we're finding the integral between negative r and r of the function, which is r squared minus x squared, all squared with respect to x. And look at the square. Okay. So, if we simplify that, volume is equal to pi integral between negative r and r. Square and the square root cancel out. So you're left with r squared minus x squared. Remember, the variable is x. So with respect to x, the variable is x. So now I've got to go do the integration. So I'm going to have pi. Okay. What's the integral of r squared minus x squared? Well, r squared is just a constant. The integral of 5 is 5x. The integral of r squared is r squared x. That's the integral of r squared x. The integral of x squared is going to be minus x cubed over 3. That's the integral of x squared. And I'm finding the volume between minus r and r. Okay, so I end up with volume is equal to pi. I'm going to have minus x, yep. Replace x with r first of all. Replace x with r. I'm going to have r squared times r. I'll replace that x with r minus r cubed over 3. Then I've got to minus the whole of, and then I've got to go replace x with negative r. So if I replace x with negative r, that's going to become r squared times negative r minus, replace that x with negative r cubed. Whoa, I often do this. Okay, sorry about that. Negative r, so replace the x's with r over here in the first part, minus, replace the x's r there, then I'm replacing them with negative r over here. Okay, so it'll be minus r cubed, okay, all over 3. And if I go up here and I simplify that a little bit further, it's going to come, volume is going to be equal to pi r cubed minus r cubed over 3. Then I'm going to have minus r cubed here times the negative is going to be plus r cubed. Okay. And then here, negative r cubed is negative r cubed times the negative is plus r cubed times the negative is minus r cubed. Okay. Minus r cubed over 3. If I add up like terms, I get volume is equal to pi 2r cubed minus 2r cubed over 3. And if I add that up, times, get a common denominator of 3, volume is going to be pi times by 3, 6r cubed minus 2r cubed over 3. And if we simplify that, we get 4r squared, 4r cubed, okay, divided by 3. In other words, volume is equal to 4 pi radius cubed over 3. And that, ladies and germs, is your formula. So we get the formula for the volume of a cube. Nice stuff there. Okay, likewise, the area could be found using integration as well. Okay. All right, guys. I gave you some exercises, some things from Mindborn Maths to do. That is the end of integration, and that is the end pretty much of paper 1. Okay. Well done, everyone. Have a good day. Arrivederci. Don't miss Liverpool too much. Goodbye.